Hi, I'm Nguyen. My student ID is 14363978. In this group project of 3, we're developing an upgrade to the traditional parking lot systems. I was responsible for designing the overall system architectures which define clearly how each of the components, both hardware and software, interact with each other, and you can see the connections in this simple graph here. I also handle all of the circuit designs and physical wirings, ensuring reliable power distributions and neat and clean signal connections between the sensors. We have IR and solar sensors, 4 servos and 2 microcontrollers, which are the ESP32 and an Arduino Nano. Finally, I developed the firmware that integrates all modules, including readings and processing the data from the sensors on board that make up the gate control logic and the assisted parking system. I also display data on the OLEDs and the wireless connectivity system, including the Wi-Fi connection to my mobile hotspot, MQTT protocols to remotely read and adjust several system parameters, and sending the data to InfluxDB for storage. These technical contributions of mine made up 90% of the projects. In terms of non-technical tasks, I have single-handedly planned the script, made the slides for the pitch, present and filmed the pitch and demonstration videos, and edited all the footages. This work results in high-quality videos that I am proud to share with my professional networks. Now, I will present the working principle of my subsystems. As you can see, the electrical system will require power from 2 different sources, one for our sensitive electronics and one for the motors. This is to prevent the chance of power spike happening in the circuit that could cause a lot of damage to our sensitive electronics here. Over here, as you can see, we have 2 main electrical subsystems. We have an ESP32 to manage the tailgate prevention servos, the 2 main servo gates, our 2 IR sensors, 2 analog push buttons, the DHT11, which is the temperatures and humidity sensors, and the OLED display. For the sonar sensors, since it is a 5-volt device, we are going to use an Arduino Nano to interface with the sensors, and this Arduino Nano will also manage our entire assisted parking system, and it will send the state of these subsystems over to the ESP32 over the I2C bus. The system state will be sent over could be whether the parking lot is empty or not, whether it's occupied or it's being occupied. For the firmware, the flow of the control system is that each lane has a pair of servo control gates and IR sensors that will detect when a car is present or has left. When a car arrives and the IR sensor can detect it, the tailgate servo will close behind the car, and the system will now wait for a press from the onboard push button, which will open the main gate to let the car in. And after it passes the IR sensors, a 3-second timer will start to ensure the car clears the areas before the gate resets. Similarly, when a car leaves using the other lane, the same sequence will happen. The gate resetting delay I just mentioned is handled in an interrupt because this is a timing sensitive operations and we want to ensure accuracy while other CPU intense processes run in concurrent with it, such as Wi-Fi and some other data uploading task. The system is connected to an MQTT broker, allowing it to receive configuration updates from a remote dashboard in the form of JSON objects, and this includes the duration of the gate resetting timer, the gate speed, the Wi-Fi channel to scan, and the minimum RSSI to locate nearby access points that meet the specified requirements. Furthermore, the user can send the SSID and password of a new network over so that the system can reconnect to this new network. The user can also trigger a network scan, and only in that case will the system publish the scan result, because scanning consumes a lot of time from anywhere between 100 and 300 milliseconds. Here, as you can see, we use a DHT11 sensors to read the temperatures and humidities around the working environment. This reading, along with the gate angles, Wi-Fi RSSI, number of cars in the parking lot, and availability of the assisted parking lot, will be displayed on a 1.12-inch OLED, and all of these will be sent to an InfluxDB data servers for long-term data storage. The code you see on the screen here is running on the Arduino Nano for the assisted parking lot, and this code is mapping the sonar sensors reading to the frequency of the buzzer. So you can see from the code if the car is within a detection range and moving closer to the sonar sensors, or it is moving away from the sonar sensors, then the delay of the beep will get mapped accordingly based on that distance. And in the case of the car being very close to the sonar sensors, the buzzer will output a long beep to indicate that the car has correctly reversed into its parking spot. For the implementation of the electrical systems, I use a proper power supply unit to separately provide 6 volt and 2 amps to the 4 servos, since the ESP32 pins can only provide around 40 milliamp max. The ESP32s and Arduino Nanos are powered using a USB cable plugged directly into my computers. Then everything is connected together on a breadboard and a jumper cable for simplicity. Here, you can see how the electrical systems are connected together on a breadboard. So as you can see, on this top section here is going to be the assisted parking lot system with an Arduino Nano and the sonar sensors on a separate breadboard. And everything else, including the ESP32s, IR sensors and other sensors and the display will be on its own separate breadboard here down at the bottom. The firmware is written entirely in C++ using the Arduino framework for ESP32, built and uploaded using Platform I/O. To control the servos, I use a servo easing library that allows me to easily accelerate and decelerate the servos in a non-blocking manner. For these specific applications, I use the motion profile following a sinusoidal curve, and the result will be a smooth and reliable motion executed by the servo. For the infrared sensors and the push buttons, they are managed using the Easy Button library that allows me to easily add signal debouncings to these sensors, greatly reducing the frequency of false signals. So if you take a look at these noisy signals here, you can see that these sections will make the button state and the IR sensor state very unstable. So debouncing will help us to get rid of those readings. For the non-blocking gate reset timer, we are going to manage it using an interrupt service routine that runs every 10 milliseconds. So that means after this function run for 300 times, this variable will change, indicating the car has reliably left its spot and the gate can be resetted. For network communications, I combine the Wi-Fi and the PubSub client libraries. The ESP32 will connect to a Wi-Fi network, which is going to be my own mobile hotspot, and then it is going to get connected to the public MQTT broker, which has the address of broker.emqx.io. And then after that, it will subscribe to a topic where control messages arrive in the JSON formats. These messages are parsed using the Arduino JSON library to update several system parameters, such as you can see the servo speed, the gate close timer, the scan Wi-Fi activations, the channel to scan, and the threshold RSSI. Furthermore, the device can also publish the Wi-Fi scan results back to the MQTT dashboard, as well as its own sensor readings and car count data to InfluxDB, allowing real-time monitoring of the system. The user should use the MQTT Explorer app to send information. Everything you can see will be sent in the JSON format with very strict syntax requirements, such as correct placement of the double quotes and commas. The Wi-Fi scan result will be displayed on the panels on the left like this. The system will communicate with the Arduino Nano for information about the assisted parking lot over I2C. It will request the information and will comprehend the data sent back from the Arduino Nano. So if it's sent as 0, it means the help slot is empty, 1 means it's being taken, and otherwise it was taken. All of our system data will be displayed using the OLED screen here. And to easily communicate with the screen, we are going to use the UHG2 library, which easily drives the screen over I2C. So as you can see, it's very simple to use. We set the cursor to choose what row and what column to write at, and we do printf to print out what sentence we want to print. The firmware will update the display once per second to show the real-time readings of the temperatures, humidities, the servo angles, the signal strength of the Wi-Fi, and the number of cars currently in the parking lot. Thank you for listening, and I hope I see you later.